that the project is being worked on. Okay? So don't just focus at 1 year. And this is figure shows, in order to define the scope, you have to take a look at the cost, resource, and time and quality. Okay? These are factors that you have to take into consideration. And finally, you can define the scopes. In terms of geographic scope, here is a guideline. So, if you want to model an area, then you will have several terminus, which are the points that the border points. So the guideline is you want to model one intersection beyond the terminus, or 3.2 kilometers away from the other end, from the end of the project. So you want to model an area, then you model a bigger, slightly bigger area. Do you understand why? That's because at the border of a model, for example, you want to modify a network like this, and you just cut this sub-area and you model it. And then you are missing the connection between the model itself and outer environment. But so the traffic flows at this borderline will not be accurate. And that's why you want to expand your model to a bigger area. Let me give you, let's give you an example like this. So here is an example. For example, you want to model this segment. Here's a construction segment or work zone you want to model. But in order to model this area, you probably want to extend the studies area into this place, and here. Okay? So just extend your network. For interstate project, here's the guideline. So longitudinal, you can extend up to 2.4 kilometers. And lateral, you probably want to extend up to 1.6 kilometers. And for arterial projects sometimes are involves signal coordination. Which means a lot of traffic signals, and they function together. So this has to be considered. Okay, consider the signal coordination impact. Task 5, plans for data collection. I want to emphasize, to collect data, certainly you want to collect data to build the model. And the data will include the network data, which includes the geometric data, the shape of the roads, elevation, and the control data, which includes the signal timing, and signalized intersections. And you also want demand data, which include the OD matrices I just mentioned, OD matrices, and vehicle characteristics, which means what kind of, how many trucks you have, how many passenger cars you have, because they behave very differently. But other than this, we have to prepare for calibration. So we build a model, and we know that the nature of our simulation model is actually a mathematical model with a lot of variables. And we have so many variables, so we need to calibrate them. And these are the data types we may want to collect, for calibration. So put this in mind. Not only building the model, but also calibrating the model. The sixth task is for estimating the cost. And cost engineering is a very complex area, which I'm not expertise in this. But I want to mention two terms. The first term is cost overrun, which means unexpected cost. unexpected cost is easy to understand, right? So you didn't plan to buy it, but finally you had to buy it. That's cost overrun. But another thing is cost escalation, which means something some elements that you need, and its price may grow up. Okay, for example, if you want to buy several licenses, and the next year they bring up the price of the licenses, that's cost escalation. So put these things in mind. The last task is called to make a schedule. So here are two diagrams or two charts. Let's talk about this first. This is a Gantt graph, Gantt chart. Gantt is a person who lived 100 years ago, and he invented this kind of chart. According to some rumor, he didn't invent this chart, but the inventor of this chart, who is Polish, didn't publish it. Okay, so we use the name Gantt graph. Gantt is a person, and in this chart we can see the length of each task and the sequence of each task. And here we will be able to see the margin, which means, for example, here you start task B and task F at the same time, but task D takes less time. So after finishing this, you have a period of time that you can have a rest. So this is called a margin. And by using this Gantt planning figure or Gantt chart, you will be able to find a critical path. So this is another diagram called PERT diagram or PERT chart. And in the center, it will be the critical path. A, E, F, for example, A, E, F, G, I. And you will easily see the critical path means a sequence of work that decides the length of the project. And here is a PERT chart. The PERT chart is not named by its inventor called PERT because there is no, because it's the acronym of Project Evaluation and Review Technology. Okay? And PERT chart has been developed by the US Navy to conduct a nuclear submarine plant in the 1950s. And you can use Microsoft Project to do all of these. And if you are not satisfied, visit this link. You will see a lot of alternatives. So I introduced these 7 tasks very quickly. Because last lecture I prepared too much, so I have to compensate today. So 7 tasks. So do you have any questions about this? I think they are very clear, and I'm not going to give you a very comprehensive introduction. I just want to point out some useful tips. Okay? Any question about that? And quickly, we go to the homework of the day. So this homework should be easy. First, you pick a group project that you are involved in. It can be a class project and it can be a real project. Then I want you to write a short essay about it. You can talk about what the project is, what your role was, and was that successful or not, and what was the reason, and how would you improve this project. But don't exceed 300 words, because I know some of you can write quite a lot. So don't exceed 300 words. Are we clear about this? Okay? Okay, if you have no question about this lecture, I'm going to resume last lecture, GIS. Okay, so for GIS, first I want to resume at the coordinate system part, because according to my survey, it's the most confusing part. So I modified my slides a little bit. I'm going to update it today, and you are going to get a new version. Please download the new version. The first thing is about GCS, Geographic Coordinate System. Okay, and we know that GCS means 3 numbers: latitude, longitude, and elevation. So after your comprehension of the ball or the sphere or the spheroid, you can get three numbers, three tuple or three number vector of longitude, latitude, and elevation for any location on Earth. Okay? So that's geographic coordinate system, or GCS. It involves three numbers: elevation, latitude, and longitude. Okay? Then we talk about the projection, the projected map coordinate systems, or PCS, or map projection. And in this part, I want to emphasize PCS is based on GCS. So you first have to select, to understand how the ball is like. Then you can choose a projection method to project the 3D thing on a plain paper, on a flat paper. Okay? Here are some examples I added. So for the same Earth, if we want to put it on a flat map, we have different kinds of projections. Understand this? I just want to show you. We have a lot of ways to put the 3D ball onto a flat paper. And these are called map projections, or projected coordinate systems. And UTM is one of them. And I added this figure to tell you how it's related to that. Okay? So if we open ArcGIS, and we add a certain layer, randomly add a layer. If we right-click this layer and choose properties, we are going to see the extent of this map, of this layer. Here is the data source. You can click this data source tab. Let me zoom in. So here is the data type, and you will see projected coordinate system. And look at its name. It has NAD 1983. NAD 1983 is the geographic coordinate system that this projected coordinate system is based on. Okay? I think if you remember, there was a coordinate system, a GCS called North American Data. North American? National? Let me check. I suddenly forgot what it is. North American Data. Okay. North American Data, 1983, is widely used in the United States. There was another famous one called WGS, 1984. They are basically the same. So these GCS are the foundation of